Welcome back, class, to Stoichiometry Problems Part 2, where we're going to tackle volume. We'll also tackle a problem that doesn't start off with mass, as most of the other problems have. And then what I'll finally do is I have a summary slide that kind of summarizes the different types of stoichiometry problems that we've gone over and some additional ones that we haven't had a chance to. Well, let's jump right into it with sample problem number 4. It's going to have to deal with volume. So how many liters? Once again, my how many, that's going to be substance B. How many liters? Now, you notice again, liters is volume. And one of the ways that we're going to get to volume is by using density. And we'll see that when we get to the end of our setup. Okay, but density relates mass to volume. And so what we're really going to end up doing is we're going to solve for the mass of substance B, and then we're going to use the density to convert that mass into volume. Well, let's go on. Are needed to react with 30 grams of iron. So again, iron is A. I'm going to mark that as A. I'm going to put 30.0 grams. Going through the next step of our problem-solving process, this would be we're starting out with mass of A, and we want to find the volume of B. And so since we're starting out with mass of A, we will see that the setup's going to start out very similarly to as it's done in the past. So I'm going to start with what was given, 30 grams of iron. I need to convert that, first step. Convert whatever unit you're given to moles of A. I'm going to use the molar mass. Divide by the molar mass. Units of grams of iron cancel. We're left with moles of A. Once again, once you have moles of A, you're going to use the magic mole ratio. And that magic mole ratio, coefficient of B, 3 moles of oxygen for every 4 moles of iron. And then what that will do, leave us with units of moles of B. To find volume, we kind of look down below here. So what we're first going to do, and we'll see it's kind of a neat trick that has to do with the way density works. We are first going to find the mass of B. And if you remember the density equation, all we really have to do then will be to divide by the density of substance B, and we'll see how that's going to get us volume of B, which is our desired quantity right here. So let's do it. All right, so to get mass of substance B, I'm going to multiply by the molar mass of whatever substance B is, in this case, oxygen, 31.998 grams of oxygen per 1 mole of oxygen. And if we stopped right there and we did the math, this would be how many grams of oxygen we would make, but we don't want grams. So let's see how our density, which is given in the problem of oxygen, 1.42 grams per liter. Let's see how we're going to do that. Well, it turns out what we need to do is we want grams to cancel, and we want to be left over with volume. So what we end up doing is divide by the density. We divide by the density, okay? And so we'll put the 1.42 grams of oxygen per 1 liter of oxygen. We can see then that grams will cancel. And then the units will be left with our units of volume. So it's all over, but doing the math. So if you take 30 divided by 55.845 times 3 divided by 4, it's in the denominator, right? Times 31.998 divided by the density of 1.42 grams per liter. This is what our calculator gives us. Rounding to 3 sig figs, we get 9.08 liters of oxygen. So in order to react with 30 grams of iron, we would need 9.08 liters of oxygen. Again, the key to this is the density equation, where density is mass over volume. But if you solve for volume, it's mass divided by density. And so the way what I say here is, if we want volume of substance B, what we need to do is find the mass of B and divide by the density. So it kind of rhymes. So when you want to find volume using density, you find the mass of B and divide by the density of B. That gets you volume. How's that? I mean, that's precision, baby. No, not really, but it's volume, baby. All right, guys, for problem number 5, what I'm going to do is I'm going to shake it up a little bit. And we're going to move away from volume for now. Although honors chem guys, after problem 5, you're going to stick around and we're going to watch a 6th problem, which is going to show the honors chem guys a second way to calculate volume. Regular chem guys, you can stop the video after we do sample problem number 5. You're only going to learn the one way to calculate volume. Okay, so anyway, let's look at number 5. What's different about problem number 5 is that for the first time, I believe in this video, we are not going to start with mass of A. So let's look at our problem. And I want to do one where we don't start with mass of A, because even though that's the most common starting unit, we don't always have to start with the mass of A. And we want to see how we're going to deal with that. So let's diagnose our problem. What mass of oxygen is needed? Okay, whatever I ask what or how many, what mass or what amount, that's going to be substance B. And so I'm going to mark, again, oxygen as substance B, and I'm going to want to know how many grams. Okay, go on to make 1.42 times 10 to the 24th particles of Fe2O3. Now, no matter how this is worded, this is the substance that I gave you the information on. And so the given substance is always substance A. And so if we want to make this much, okay, 1.42 times 10 to the 24th particles of this, we might want to know how much to start off with, how much oxygen to start off with. So if we look at the diagnosis, this is a particles of A to mass of B. And as we mentioned before, when we hear the word particles, what are we thinking? I know you just said it at home, Avogadro. And when we're talking about mass, when we're thinking about mass, we're thinking about molar mass. You got it, you got it. So we're going to need Avogadro's number. And we're going to need the molar mass of substance B, again, the molar mass of oxygen. So let's get this baby started. We'll always start with what we're given. Okay, again, starting with what we're given particles of A. Again, what's the next step in stoichiometry problem solving strategy? It's to convert whatever units you're given for A into moles of A, and to go from particles to moles. You got it. We're going to need Avogadro. See, there we go. We're left with moles of A. Again, moles of A, you're on your way. Once you have moles of A, you're ready to apply that magic mole ratio, which will then turn our problem from being in terms of substance A, which we really don't want to know about. We already know about it. We want to turn it into, have our problem in terms of substance B, which is what we want to figure out. So that's why I call it the magic mole ratio. Once again, it's going to be the coefficient of B, 3 moles of oxygen from the ballast equation, for every 2 moles of Fe2O3. Again, moles of Fe2O3 cancel out, and lo and behold, the magic mole ratio did its trick once again. Now our problem, the units that are left over are in terms of moles of substance B. Okay, once we have moles of B, do we want moles of B? No, we want mass of B. And so, again, moles to mass, molar mass, and it's going to be the molar mass of oxygen. Again, apply the molar mass. Moles of oxygen cancel. I'm left with mass of B. It's what I want. Cha-ching! It's all over but doing the math. So 1.42 E24 divided by 6.022 E23 times 3 divided by 2 times 31.998. Again, you know me, I like to do my math when using the factor label method in the order that it comes, that they appear in the picket fence setup. Rounded to 3 sig figs, 113 grams of oxygen would be needed to make this many particles of iron 3 oxide or rust. So again, even though this problem did not start out with mass of A, our first step was to go to moles of A. And if you're starting out with particles, well, you're going to use Avogadro's number to get to moles of A. Once you have moles of A, as I said, you're on your way. The rest of this is kind of prescriptive. You then apply the mole ratio. Whatever units you want to end up with, you use that as your last conversion factor. And since I wanted to end up with mass of B, I use the molar mass of B. Let's say I wanted to find out particles. I would use Avogadro here, okay? And if I wanted to find out volume, I would find mass of B and then divide by the density of oxygen to get the volume. So you can see that this problem-solving setup is very versatile. You can end up calculating many different things using the same setup strategy. Okay, so regular chem guys, you can stop the video here, but honors chem guys, we're going to go on and learn a second way to calculate volume. All right, honors chem guys, thanks for sticking around. You may have wondered as we were going through this, we hadn't mentioned the molar volume. Well, guess what? You can use the molar volume to calculate volume when your substance is a gas and when that reaction happens at STP. So there is a place for the molar volume. It's only a special case. You can only use the molar volume, as we did before in the last chapter, when your substance is a gas and when the gas is at 0 degrees C and 1 atmosphere pressure, also again known as standard temperature and pressure. But if your reaction is done at those conditions and your substance is a gas, you can use the molar volume to calculate volume instead of using the density. Okay, and so let's see how this shakes out. Okay, doing the diagnosis. How many liters of oxygen? Okay, so that's B. How many liters? I notice that oxygen is a gas, and as I read on, I notice that it says at STP, and so I can find liters at STP. Go on, are needed to make 110 grams of Fe2O3. So this is my known, this is my A, this is the amount I'm going to start with. So looking at my units to do the diagnosis from my 6-step problem-solving process, this is a mass of A to volume of B, because B is a gas at STP. It's going to be volume of B at STP. Okay, let's start with what we're given here. I'm going to start out with mass of A. I want to get to first step, get to moles of A. I'm going to use the molar mass of Fe2O3. Okay, molar mass, 159.687 grams per 1 mole. Again, I'm left with moles of A. I'm ready for my magic mole ratio. Apply my mole ratio. Moles of A cancel. And I'm left with moles of B. Now, if you guys remember from the last chapter, when you have moles, you can actually go directly to volume using the molar volume, which is 22.4 liters of oxygen per 1 mole of oxygen. You can see you can actually just go directly to volume. You don't need to go to mass of B and divide by the density, because the molar volume is a direct relationship between moles of oxygen in this case and liters of oxygen. And now it's all over, but doing the math. So let's complete this problem right now. Okay, so 110 divided by 159.687 times 3 divided by 2 times 22.4. Here's what my calculator gives me. I'm going to round it to the 3 sig figs that my problem started with. And the answer, 23.1 liters of oxygen. So that is how much oxygen you would need to make 110 grams of Fe2O3 in this balanced equation. All right, guys, that kind of wraps it up for here. I'm going to record stoichiometry part 3. And in stoichiometry part 3, it'll just be a short video that will summarize all the different types of stoic problems that we've done, kind of in a one snapshot, you'll see. And then you can refer to that, that graphic that I'm going to show you when you go to do your homework. Okay? All right, guys, good luck. Zoom you soon.